Hello scholars, per request here is my face as well as my voice for you. Let's start our review for applications of differentiation. Okay, so go ahead and read the do now. I'm going to read it out loud for you. The rate at which a baby bird gains weight is proportional to the difference between its adult weight and its current weight. At time t equals 0, when the bird is first weighed, its weight is 20 grams. If B of t is the weight of the bird in grams at time t days after it is weighed, then dB over dt equals 1/5 100 minus b. Let y equals b of t be the solution to the differential equation above. So this is the differential equation. With initial condition b of 0 equals 20. Okay, so there's a lot of information here. We know that b of t is the weight. Now, that means that dB over dt is the rate at which the bird is gaining weight. Cool. Part A says, is the bird gaining weight faster when it weighs 40 grams or when it weighs 70 grams? Explain your reasoning. So you can go ahead and pause the video and try out something here to figure out the answer. So what I'm going to do is take 40 grams and plug in dB over dt, because I'm going to get the rate at which the bird is gaining weight. When I plug in 40, 1/5 100 minus 40. Then I'm going to do the same for 70. And see which one has the greater value, because that's going to tell me which one has a greater rate of gaining weight. Okay, I'm going to do the work here. So I have, for the first one, I have 1/5 100 minus 40 is 60. 60 divided by 5 will give you 12. So for 40, 12 is the rate at which your bird is gaining weight. Okay, so that's going to be your grams per days, because it says here grams and the time is days. Let's do the same for 70. So I have 1/5 times 100 minus 70 is 30. You divide that out, you get 6. So I have 6 grams per day. That's how much the bird is gaining weight, 6 grams per day. Which one's greater? Great. So you say the bird is gaining weight faster when it weighs 40 grams. And you are all good. Okay, the main focus of the review today is applications of derivatives. Okay, so it's important in calculus to study the applications of derivatives to the understanding of characteristics of graphs and of functions. The first thing we learn for applications is maximum and minimum. So we also call this critical points. All right, so that's peaks and valleys, meaning top and bottom. It usually occurs when the derivative is equal to 0, or if the derivative is undefined, meaning pointy top or bottom. Okay, so all that means, if I have a graph, let's say this is my graph, the very top here, the derivative is 0 because the horizontal line is flat, meaning the slope is 0. In the very bottom, the derivative is also 0 because the slope of the line, tangent line, is 0. Sometimes you have pointy parts, like let's say this part is a pointy part. Then that means at the tippy top of it, the derivative is undefined because of the pointy part, meaning my line could have been this way, could have been this way, could have been this way, could have been multiple ways. All right, the extreme value theorem, we're going to review that later on. It reminds us to check the endpoints when you're considering a function in a closed interval. All that means, if I have a closed interval, let's say a graph that starts here, goes like this, you have to look for the max and min, so you can see the minimum is here, the local minimum is here. But you also have to consider the endpoints, like this end could have been the max, which in this case, it looks like it could be the max. Okay, so you have to not just look at the peaks and valleys or top and bottom, you have to look at the ends, because maybe the ends gives you the minimum or maximum. Okay, so extreme value theorem says check endpoints. Great. Increasing and decreasing. So increasing, when the part of the graph is increasing, meaning going up, the derivative is positive or above the x-axis. So let me say that again. If I have a graph, I have a part of the graph that's increasing, so the part of the graph that's increasing has a positive derivative. Meaning if I drew the derivative of this graph, it has to be somewhere above the x-axis. Okay, this is above the x-axis. So let's say this is the derivative. This is the function. The derivative of the function has to be above the x-axis. So this is above, because I said positive. Now, it goes the opposite way for decreasing parts of the graph. So let's say this part is decreasing, going down, so that means the derivative is negative. Meaning, if I look at my picture, the part that goes negative has to be below the x-axis somehow. Okay, so it crosses here at 0, which makes sense because at this point, this is a max. So it has to cross the x-axis because it's 0. And then afterwards it's negative, so it goes below. So this is below. Okay, those are just some reminders. So a quick reminder, there is a first derivative test. Also, there's a second derivative test, okay? We're going to go into the second derivative test. The second derivative test says, if you have a function and you know that you have a critical point, meaning the first derivative equals 0, and the second derivative there is positive, then you have a local minimum. Okay, meaning when the second derivative is positive, we have to remember that that means concave up. So, if I have a graph, and I know that I have a critical point, so let's say here, I have a critical point, meaning f prime of x equals 0 here. But then the second derivative here is positive. That means the graph is concave up. Then essentially you have to have a minimum. Because you're concave up, that means there's a bottom, and it has to be a minimum. The second derivative test also says that if you have a critical point, so same as earlier, and the second derivative there is negative, meaning concave down, then you must have a maximum there. And the explanation here is the same. So let's say I'm looking at my picture and this is, the critical point here is this dot, and the second derivative there is negative, meaning I'm concave down. Then this point has to be a maximum. So that's the beauty of the second derivative test. It mixes in the information we have from the first derivative, meaning equals 0 for the critical point, and the second derivative. So if it's positive, it's concave up. If it's negative, it's concave down. So you're mixing those two information. Now the test fails if there's three ways it fails, meaning it doesn't tell us anything. If the first derivative equals 0 and the second derivative equals 0, doesn't tell us anything. Okay? It could be inflection, it could be critical point. It also doesn't tell us anything if the first derivative is 0 and the second derivative does not exist. Doesn't tell us anything. It doesn't tell us concave up, concave down. The third way it fails is if the first derivative does not exist. Then we can't even check the second derivative. Okay, so these are three reasons why it fails. No information. Okay. Okay. A few more about review. There's three theorems mainly that show up, and we need to make sure that we know what's going on. The first one is something we already discussed, the extreme value theorem. It says, if a function f of x is continuous on a closed interval, so if I visualize that, make any function, so that's continuous on a closed interval, so let's say it keeps going up here, that means it starts from a number, let's say a, and it ends on a number b. That's what closed means. It doesn't keep going forever. Then, the function has to have both a maximum and a minimum. It just has to. Okay, it has to have a maximum. It has to have a minimum. And you have to check the endpoints too to consider. Okay, so maybe the endpoints is the max or min. Maybe it's somewhere in between. In this case, in the picture, this is the minimum, which is somewhere within. But then you also have a maximum, which is an endpoint. Okay, so you have to check. The other theorem that shows up is the mean value theorem. Okay? If a function f of x is continuous on a closed interval, a to b, so same thing, you have a function, it starts at a, ends at b, can be anywhere. This is just an example. And it's differentiable, meaning no pointy parts within that interval. Then there is a number such that the derivative equals the slope. Okay, so that means take a, take b, take the slope of the line that connects them. So that's the slope. Then somewhere in between, there is one point at least that, let's say, the derivative at that point is this exactly equal to the slope from a to b. Let me say that again. When you get the slope from a to b, let's say that's 17, there's somewhere in between here that the derivative of that point has to also equal 17. That's what the mean value theorem says. Mean means average, so you can kind of connect it with the slope, getting the average. Okay, so find a way that you can recall this theorem. Okay, intermediate value theorem, very last one. Let me read it first, okay? It says, if f of x is continuous on a closed interval a to b, and m is any number between f of a and f of b inclusive, then there's at least one number x on the closed interval such that f of x equals m. All that means, let's say I have a graph, okay? It starts at a, ends at b. And I know that, let's say, the y value up here is pretending to be 5. The y value down here is pretending to be, let's say, -3. Then if I ask you, is there one point in this graph such that the y value is, let's say, 2? Such that the y value is 2. Then you say yes, absolutely, because 2 is between -3 and 5. So at some point in this graph, you're going to have to cross 2.